Hello, my name is Greg Gorbett,
I'm Shijin Karumal.
and we are here to discuss the results of our NIJ funded grant work titled Experimental and Numerical Investigations for the Prediction of Depth of Calcination of Gypsum Plasterboards Under Fire Exposure. So, as fire investigators, we recognize that gypsum plasterboard or drywall is what is more commonly known as is something we look for as to identify damage and fire patterns. And from that, we can get degrees of fire damage. But oftentimes, the damage is too much that we can't observe it anymore, and measurable damage becomes one of the things we start looking at as fire investigators. So, the study here is we wanted to be able to try to compare between the depth of calcination and total heat exposure, which helps us as in the forensic side of fire investigation. So the objectives was to evaluate or analyze gypsum calcination and the prediction of depth of calcination. There are several challenges associated with this. One is the thermochemistry and endothermic dehydration of gypsum itself, the heat, mass, momentum, and species transfer through the porous medium, and the variable thermophysical properties and heating rate that is associated with exposure of the drywall to heating. So let's discuss the basics of gypsum calcination. So when drywall is heated, essentially gypsum is calcium sulfate bihydrate, and it's 21% by mass chemically bound water, and it also has absorbed free water. So when it gets heated up, without going through all the details of it, essentially you start dehydrating the drywall. And that dehydrated drywall or gypsum becomes brittle, and then we can also, as fire investigators, measure that. And one of the things we use to measure that are depth calipers. The depth caliper that we used in our experimental series is shown at the bottom of the screen. It's a digital depth caliper with a constant force spring internally. So we performed a series of experiments with controlled heat flux and duration of exposure. We started with a radiant panel, and so on the left photo, there is a radiant heat source. That panel was exposed to a 2 foot by 2 foot drywall section of drywall. In the drywall, we have mounted Type K thermocouples, and we did that in a in a every millimeter from the surface. So we took the temperature at the surface, the exposed surface to the heat side, all the way through the drywall, which is a 1/2 inch drywall, so 12 millimeters. And we went 1 millimeter in depth um, throughout the board. Um, so we did the radiant panel, and we had various constant heat fluxes and durations from that. We then did a pre-mixed burner. In the middle photo here is a pre-mixed flame that we expose the similar sized drywall to. And then our last series of experiments that we did with heating is this diffusion burner that we used a gas burner and exposed the drywall to the diffusion flame. The depth of calcination was measured every minute of exposure, and we plotted that data in our experimental results. For the rest of our results and everything, if you look on the right hand side of the screen, there is a cross section view of the drywall that we've made it as an illustration. And the orange arrow on the left is essentially the side of heating. And so we'll have one thermocouple there, and then 1 millimeter in depth all the way to the back side, or what we've labeled here as ambient. 12.7 millimeters is the thickness of 1/2 inch drywall.
In addition, thermogravimetric analysis, differential scanning calorimetry, and Fourier transform infrared spectroscopy were also conducted. The TGA results were gave the mass loss as a function of temperature, for different heating rates. This helps us develop variable heating rate thermochemistry models. DSC will give us effective heat capacity, and FTIR is useful to understand the effect of calcination by doing FTIR analysis of gypsum samples exposed to heat flux and not exposed to heat flux.
The experimental results we show in a couple different ways. So we took temperature readings internally of the drywall every 1 millimeter into the drywall. So there is one that's mounted on the exterior, the heated side, and this is the blue line. That's the 0 millimeter mark, and it's the highest temperature on the chart, which is expected. And then we go every millimeter into the thickness of the drywall from there. We see on the exterior side where it's facing the heat source, we see a spike in temperature as the paper begins to pyrolyze and then later burn on that side. So the combustion of the paper shows a spike, and you'll see this consistently in our work. But then internally, you can see the temperature slowly rise throughout. And this is the 20 kilowatt per meter squared radiant panel test. Another way of showing that is the contours that occur internally, and that's shown on your right here.
We also calculated, try to understand the experimental uncertainties. So we looked at standard deviation, the actual values of standard deviation, and the standard deviation as a percentage of the mean temperatures. We found significant deviations because of local irregularities in the gypsum board and experimental and measurement uncertainties, up to 15% deviation for lower heat fluxes, and that even increases further when we did experiments with turbulent flames and high heat fluxes. Then we looked at temperature of the dehydration front. As this is very difficult to directly experimentally measure, we measured temperature at every millimeter thickness, and we measured the depth of calcination. Based on that, for each minute, we interpolated the measured temperature data for the measured depth of calcination to find the temperature of the dehydration front. Here, the TGA results are shown for different heating rates. So the mass loss is plotted as a function of temperature, and on the right hand side we have derivative of mass loss as a function of temperature. At lower heating rates, it gets more time for the same temperature difference, thereby showing a larger mass loss. Mathematical formulation, we assume gypsum board as a homogeneous porous material, and we looked at gypsum chemistry, which happens over 2 steps, and species conservation equations for both water vapor and air, and momentum conservation equation using Darcy velocity vector, and energy conservation equation that considers both the solid part, the water vapor and air, and effective conduction, the mass transfer because of both concentration gradients and pressure gradients, and also we consider the source term. The most difficult part of this is the source term in the species conservation equations for water vapor as gypsum calcinates the chemically bound water gets released as water vapor. So this needs to be accurately predicted in order to model gypsum calcination. And we need to have gypsum thermochemistry models to model the source term in the species conservation equation. So for that, initially we looked at from the literature some TGA data at a constant heating rate, and we converted that in terms of as a function of temperature to a function of time, and we developed Arrhenius type of numerical equations as a function of two Arrhenius coefficients A and B and remaining water content in the gypsum board and temperature. We compared that for two stages of the gypsum calcination, and we continued that analysis with our own TGA measurements. We calculated the A and B coefficients, and the equation contains the, the water vapor content from the TGA data, the coefficients we calculate, and a time integration of the source term up to the previous time step. And once we have that, we add that to the species conservation equation and corresponding NIJ absorption will also be considered. Here is a comparison of the variable heating rate gypsum thermochemistry models, reaction rate predictions, and experimental data from the TG analysis for different heating rates. So for 10 and 20 Kelvin per minute heating rate, we have a higher heating rate here, and at heating rates 800 Kelvin per minute. Throughout a wide range of heating rates, we are getting reasonably good agreements. Further details of the numerical model include solving mass, momentum, and species transfer using a finite volume method, using central difference for conductive and diffusive terms and upwind for the convection term. Initial conditions are we are assuming a methane air stoichiometric flame, and one side is exposed to fire or heat flux and the other side is ambient. We compared numerical predictions from the model with experimental measurements for a selected trial for different heat fluxes. Set a lower heat flux of 10 kilowatt per meter square. We see reasonable agreements, even though and most of the numerical predictions are within the experimental uncertainty. The same trend continues. And even at very high heat fluxes, the fluctuations in the surface temperature are significantly higher at very high heat fluxes. Despite that, internal temperatures are reasonably well predicted. We also conducted sensitivity analysis of key modeling parameters, both using local sensitivity analysis, which considers how much variation happens for a 1% change in that local variable, and also global sensitivity analysis, which considers the net effect of that parameter in the total variance. And both studies show porosity and initial density as the most sensitive parameters.
We also did scanning electron microscope images of dehydrated gypsum wallboard versus newer drywall, and we found that there is a significant amount of local irregularities within the drywall, but we did find that the SEM approach is a potential method of evaluating the drywall that's been dehydrated.
So we also developed a numerical model based on the 1D model. The three-dimensional model is very similar to the one-dimensional model, except that it considers both length and width of the gypsum board. And now we can simulate non-uniform heat fluxes. The 1D model can only work with uniform heat fluxes. We simulated non-uniform heat fluxes, but as we can see, the differences from the predicted from a constant heat flux or a uniform heat flux and predicted from a varying heat flux using a 3D model for locations, selected locations, are very similar. That means the problem can be reasonably approximated as a one-dimensional problem. This is because the gradients along the depth are much larger than the gradients along the length and width of the gypsum board. So hence, except very close to abrupt changes in heat fluxes, most of the gypsum board can be reasonably, or gypsum board calcination can be reasonably approximated to be a one-dimensional problem. We also developed correlations connecting depth of calcination and heat flux, as these correlations actually depend on a large number of parameters, including exposed heat flux, boundary conditions, initial conditions, and heating rates, history of heat flux. We try to simplify those variables and try to come up with approximate and simplified equations connecting heat flux alone. So these equations give, once it reaches a near steady state, what will be the depth of calcination when exposed to that particular heat flux. And we developed correlations, and the second part of that correlation, that's 1 minus e power t by 100, that's a correction factor if the time is exposed duration is very small. If the exposed duration is more than 8 minutes, that part goes to near unity, and when the duration of exposure is very small, this entire equation is needed.
The last step in analyzing whether or not the numerical model and the correlations fit a full scale experimental series, like a practical application of it, we compared a full scale compartment fire test, and you see in the top right corner a diagram, essentially fire starting in a sofa along the right back wall. We are comparing in the shots here of depth measurements on that wall to a plot developed from Fire Dynamics Simulator. We then compared that to experimental correlation and the numerical correlation, and they all show a reasonable agreement in the general trend or pattern that the depth measurements from the actual experiment show to that which is a plot of heat flux from FDS to both the experimental correlation and the numerical correlation.
So what we did is we looked at the heat flux from the FDS, used that as an input for our own numerical correlations, then calculated the depth. So the error, the deviations we are seeing could be either because of the experimental and numerical study we used to develop the correlations, and the correlations and the errors with the FDS. So the deviations are a combined effect of all this.
So that ends the presentation. I know it's like a 30,000-foot view overview of what we've done and the results from that. Obviously, we'll have a full report that's published with NIJ and several conference proceeding papers as well as journal articles that will come out from this work. But if you have any questions in the meantime, our emails are listed here at the bottom of the screen.
Thank you.